Okay, so thank you very much everyone for coming, and thank you for anyone who's watching us on the internet. So this is our second set of design talks in our Manchester, Southampton, Glasgow joint series. The first were in October in Glasgow. So we have 3 talks today with the schedule we've got here. And we'll have a tea and coffee break in the middle. People in the room can obviously ask questions at the end of each talk, but if there is anyone watching who wants to ask a question, then if you tweet hashtag #AskMSG, we'll make sure that the question gets asked. Okay, so without further ado, maybe we should. We'll crack on. So without further ado, we'll go to our first speaker today, who's Werner Müller from Johannes Kepler at University of Linz in Austria, and he's going to be talking about approximate Bayesian computing design. Thanks, Werner.
Thank you very much.
Oh.
Fine. Well, thanks everyone for coming to my presentation, and thanks for having me. Thanks for having me for the sabbatical here in Southampton. It's really been a joy so far. And I'm going to give you a little bit, probably some of you heard me already talking about this topic, ABCD here, and I'll try to give you first an overview and then some new developments on latest research on this topic. Yes. So what is ABCD? It's an acronym that we created out of, obviously, the existing approximate Bayesian computation acronym, and we put the design at the end of it. So that's where the D comes from. And we perceive it as a convenient way to deal with difficult probability models and complicated model criteria, way of designing experiments. What we need as prerequisites, you will see, you will just need a probability model where you can simulate from, and you need a prior distribution for your parameters. And it's loosely based on the techniques of simulation-based optimal design that were proposed by Müller in the 90s. It's not me, but my namesake, Peter Müller, is also from Austria. And there is a story to the whole ABCD stuff. It mainly formed the PhD project and thesis of Markus Heine, who is my PhD student and who promised me to watch this presentation today. So hi, Markus. Hopefully he doesn't, pose any questions by Twitter. Okay, so the story of this project was the following. We had, I had met Henry Wynne in Cambridge at the Newton Institute special semester in 2011, and we came up with this, idea of using ABC for optimal design purposes, and then we wrote up a joint research proposal for the Austrian Science Fund, and we brought in the proposal. We also wrote the first paper on it, which was published eventually in the Mueller proceedings in 2013. This is the Heine et al. 2013. And then one of the referees of the project proposal wrote, that's good project, it will work, because I know it will work. I just supervised a PhD thesis in Australia who did the same thing. And this was this guy, Christopher Wandy, who did, quite similar stuff, which we were not aware of. And it was also published by Wandy in Petit 2013. So independently, this thing really was developed. In the meantime, we have met with Chris and with his group, and we are trying to, join efforts in forwarding this method and making progress in this method. I think it's quite useful to me. I don't know. So let me give you some introduction, and to get things right, let us put it into the Bayesian perspective, Bayesian learning perspective, which is the sort of the framework for all of this. This is mainly put forward in a joint paper by Marcus Henry, mainly Henry, and me from in Entropy, which was published in Entropy in 2014. Well, and you know, how are the Bayesian design criteria, the useful ones, constructed? They are in principle constructed or can be perceived that we have the posterior distribution, and we have some general function of the posterior distribution that we want to optimize. And what we're looking at is the pre-posterior expectation of this posterior distribution, or of this function of the posterior distribution. Okay? And we can characterize these functionals that are useful in this respect. And it's quite rather simple to see that the class of all convex functionals, you know, forms sort of the reasonable class, because this would be the class where we would be learning from through the experiment. So the class of functional where we've been learning, and we can express this like this. So where the pre-posterior expectation u would be always larger, or at least as large, as the design criterion that is evaluated at the prior distribution. Okay, so this would be the information before the experiment. This would be the information after the experiment. Information after the experiment is always larger, as long as you use suitable phi here as a design criteria. Okay, and all the design criteria that we can reasonably use, well, are criteria that fulfill this requirement. So this is the embedding of the whole thing into the Bayesian learning perspective. And if you want to know more about all this stuff, you will find a full discussion in this paper. So let us move now to the ABC part. Some of you might not be familiar with approximate Bayesian computation, so I'm going to say a few words about it. Well, in principle, if we have a design criterion available, or we can estimate the design criterion. So if we have the phi, or we can estimate the phi, yes, then what we could do is we could perform Monte Carlo integration to get this this integral here, and then we can then we have an estimate of our expectation that we're interested in, and we can proceed by maximizing this expectation by using some design algorithm or some routine to find good designs on this criteria. Okay, this is essentially the setup that Peter Müller already had in the 90s for doing his simulation-based designs. Okay, the problem comes now. What do we do if estimation of phi is not possible, intractable, or it's too complex, or whatever? Yes. So this is what happens if the distribution. What happens if the likelihood is not available to us for any reasons? Then the one suggestion that has been put forward in the literature is to use this technique called approximate Bayesian computation. And how's this? How does this work? Works in the following way. So you have, and I'll give you the simplest version of it. Okay, that's what they call the ABC rejection set. Okay. So what are you going to do? You need a prior, of course. Yes. So you have this pi of theta as a prior. Then you draw a theta from this prior. Okay. Then you draw an observation from your generating your probability model. Okay. Then you look whether your observation, yes, that your new observation that you just generated is close to any of the existing observations that you have. You need a definition of closeness, some kind of definition of closeness. So you're looking actually in the neighborhood, some well-defined neighborhood of your existing observations. And you accept theta if your new observation, your generated observation is in the neighborhood, and you reject it. And the collection of all the thetas that you get from this simulation, of course, forms you something which comes close or approximates the posterior distribution. So without knowing or using the likelihood, you can generate the posterior distribution or approximate it. Okay. Of course, there is a certain special role that is played by this neighborhood. Yes, and there are two things. The neighborhood could be small, very small. Actually, it could be just the data. Could be just the neighborhood. Yes. Then, of course, you almost never accept theta because the probability that you really hit an old data point by a new simulated one is 0. Okay. So if the neighborhood is too small, the whole thing runs and runs and runs. If the neighborhood is too large, of course, you always accept theta and you don't learn from the prior. Yeah, there's no change from the prior. Because you never reject. So you just reproduce the prior. Okay, nothing else. So these are the two extremes. Okay, and in between lies some well-chosen, useful neighborhood that will give you a nice approximation to the posterior. And there is, of course, a huge literature about this. Okay, the method was proposed by some geneticists in the 90s and has been taken up from the in the statistical literature since then. And there are a lot of refined methods of doing approximate Bayesian computation. I'm not going to go into detail very much in this presentation. Of course, when you're high dimensional, you cannot also very easily look at what is a close observation to a real observation, especially when the dimensions are quite larger than, I don't know, 3 to 10. Yeah? Then you need something like you need some summary statistics that you look at, and then you look at some observations that are close in the summary statistics to the summary statistics of the data. Okay? And usually use, if you know them, use efficient statistics and means, variances, and so forth. But in all the examples that I'm going to show you, I think we'll do with the original observations. Not quite true. Okay, not in those. Okay, so this is ABC. Now, what is ABCD then? What is the problem we're having here for using this in design? The problem is we don't have data. Before you do the experiments, there's no data. Okay, so we don't have any Y's here. So how can we use it still for experiments? Oh, we just generate the data. Okay, let's generate the data. Let's fix a design. Generate the data, true data, which is of course not true. Then do the ABC, and then generate new data. Okay. So all we do is we put the ABC step or ABC part into an outer loop where we generate data from a design experiment. Okay, that's ABCD. It's a very simple idea. Yes. So we have an outer loop now here, and there is this. So we produce a sample of the size H, and we produce a sample of the size G, which are the two loops. The one is the, if you may say so, the D loop, and the rest of the ABC loop inside. Okay, and you just do what I just described. Okay, but you're not using the true data, but you're using these data Y to the I here. Okay, all the rest is just a straightforward extension. And you repeat this, and you have to repeat it many times. Already from this slide, you see that this is a very computationally intensive procedure, because already ABC is a computationally intensive procedure. You have to produce these, simulated data. You have to prepare, and now you have to produce this outer array, if you may say so. And then again, you have to do this in some sense for every potential design point, or for every potential design. Okay? Although we'll do more clever things than this rough outline here. But in principle, this is the idea. Now, one step ahead, one easy step ahead is not to do this in a loop, because this will take, this will take too many resources in any kind. So one way out of this is to do a pre-simulated sample, very big one, and then to reuse the same sample all the time. Okay, that's what we've been doing. So there's a really big sample, I call it S here, of size R, and we use ABG rejection sampler here. So we order the sample pertaining to some designs, and then we look at the distance. Yeah, we always have to define what a neighborhood entitles. So usually what is done is you calculate distances between design points or observations, and then you look whether the distance is below a threshold or something. This is the easiest way of defining such a neighborhood. But you could define neighborhoods in other ways. That's what we're doing right here. Okay. So you're just slicing up this big sample, and reuse the big sample for all these steps in all the sequences. Yeah, just to save, I would say, save generating new data all the time. It's just taking unnecessary resources here. Okay, then another version is a version proposed by Marcus is not using, this simple rejection sampler, but using something like an importance weighted version of it. Be more likely to hit, more important regions of your simulation space that you need to cover. So you have weights now, and these weights will be proportional to this simulated distribution that you're using, and of course this again you get by here we have now k instead of n. It's just a slight maybe subtle change in notation. N would be just a neighborhood, very fixed neighborhood. K here would be something like a kernel, which smoothes out observations that are far away. So you can play, with all these elements a little bit. You can play with the size of the neighborhood. You can play with the form of the kernel that you have, and you can, play with the weights that you're generating. All these kinds, all these elements will affect the procedure and the effectiveness of the procedure in one or the other way. But again, we're using a pre-simulated sample that turned out to be the easiest way of overcoming the size of simulation problems. But you will see that in the examples that we'll still have problems with capacity. Okay, another question is also how to choose the epsilon, how to choose what is small neighborhood, small enough neighborhood. Of course, you could fix the epsilon at some value, just let it run. That's what we at the beginning did. Then Marcus said it's better to use probably something that is it's called the effective sample size, so that you sort of fix the neighborhoods such that you have a certain sample size that conforms to an equivalent number of independent observations. Yes. So, so you fix in some sense the amount of information that you have for every neighborhood. This is slightly better because in this way you're guaranteed to have at least a certain number of observations in the neighborhood. You don't. Otherwise, when you fix the neighborhood, it could be empty. Okay. Okay. So these are the tuning parts, things that you can play around with. Now let me come to some of the examples to make things maybe more understandable, and maybe also you can relate to it through the examples more easily, and I hopefully can show that things really work well in most instances. Well, the particular problem that we're still having even in this example is the problem of capacity. Yes, that's the only bottleneck really. I mean, if you would have really big, large, powerful computers, more than we have now, all this would be no issue. But let us start with a very simple example, that's quadratic regression, because we all know what the results must be there. And the setup here is a Bayesian setup. So you have your observations generated from we assume here a normal distribution, and the model that we have is a quadratic. So it's a quadratic in one factor. So every row is always 1 xi and xi squared. Okay, and then you have prior information for the theta, which is again normal, and you have a prior precision matrix R, which that gives you the amount of the prior information you have. So what we of course now know is when this is a prior information that doesn't provide you any additional information, so that is a flat, whatever flat prior that you're having here, then what you get as an optimal design here for this case is of course and we're in the region between -1 and 1. So what you get is design at the edge points and at the center, -1, 0, 1. Now we can play around a little bit with the prior information, so we can set the prior information such that it assumes, generates the information at certain points. Okay, and that's what we're going to do to make this example a little bit more accessible. So the prior information now will be fixed so that we already have some information from points -1 and 1. Okay, R needs to look like this. And then the optimum, of course, will be at the point x0. This is just to make things easy to compute, and we really have to compute only one point here. And also, what is the criterion that we're using? I haven't said anything about this. We would be using some equivalent to d-optimality or Bayesian d-optimality, and this would be using the Kullback-Leibler divergence or the Shannon information as stated here, because this would give us exactly the Bayesian d-optimality criterion that we are quite familiar with. Okay, so we're using this as a design criterion, respectively the integral, of course, over it. I never know whether I should call this the design criterion or this the design criterion. Bayesians, I think, call this the utility. So, okay, I could call it the utility. So, yes, by using this, the optimum should be at x equals 0. And now from the next slide, I can show you how our results look like. So this would be one of the baseline results here. This you see is, so for every point here now, or for a grid of points, we calculate this utility. Okay, and of course at point 0 there should be the maximum utility. Oops, sorry for that. And this is a baseline calculation which was done with 1,000 for the outer loop, I believe, and this is the inner loop of 100,000. So it was still quite feasible because we just were looking for one point. So now you see also on this graph, how things change when you change some of the tuning that is done. For instance, here when you double, of course we selected neighborhood which provides us with good results. And we just double the neighborhood here, and things go very bad. Okay, so neighborhood obviously is something very important here, so and especially to get the neighborhood right. So this was a sort of a borderline neighborhood. We've been changing the, reducing the number of of computations into 2 loops, and things went slightly worse, but not as bad as changing the neighborhood, at least in this example. Okay. Well, you see, you need quite an amount of computation, even in this simple example, to get things going. So this was the setup example, I think, that I just gave, because you're probably quite familiar with everything that's going on here. Let me give you maybe something more realistic or more advanced example. This is an example about spatial prediction. It's actually taken from one of my earlier papers with a colleague of mine, Helmut Weidler and Luc Bronzato from 2012. And it's about computing the predicted distribution of a new observation yn plus 1, given that you have already observations up to n, but these observations are spatial observations, so they are, they are typically spatially correlated by a pre-given correlation function. And the criterion of interest is now the maximum variance of the predictive distribution over the design space. This is classical. Or in other terms, if you want to put this in these classical geostatistics or spatial statistics terms, this is what we would be doing is a Kriging prediction, and we would like to minimize the Kriging variance. Okay, this is what's done here. So now again, simple example out of it, but one that I think shows quite a nice feature, is we have now 4 observations. Actually, 3 observations form the design, and we're looking for where to take the 4th of these observations. And we're having a 1-dimensional Gaussian random field with mean 0, and a so-called exponential correlation function, which looks like this. The correlation function is just a function of the distance of the points, and we have a parameter here in exponent. Okay. So this is a very frequently used setup in spatial statistics. It's not an uncommon setup. Of course, we're using a 1-dimensional example here because I can easily. We did also 2-dimensional case, which is the standard case. But here it's easier to show you the features of things. Okay, so what happens here? Here there's a strange effect, an effect that was investigated by many people. That is because when you're using the Kriging variance, the classical Kriging variance as the design criterion, you're doing what? You usually forget that you need also to estimate this parameter theta. This is always neglected. The Kriging is always done as if this theta was known. Okay? But of course, what you usually do in spatial statistics is, with the same data set, from the same data set, you also estimate this theta. Okay? So you're introducing additional uncertainty into the problem that is not accounted for by the design criterion. Okay? So you using the Kriging variance is not a very good idea, especially for small numbers of observations. That's the problem here. We have just 4 observations here. So you can look at this graph. Here we have 3 observations, one at -1, one at 0.5. Oh, sorry, it's 0.5 and 1. And when you plot the Kriging variance, this is the reddish thing here, you get this. And this seems to really give you or justify the space filling arrangement of these 3 points. But this is not the true variance really, because this is the variance which ignores this additional uncertainty. So to include this additional uncertainty, there have been several proposals of many people. One of the proposals was what Zimmerman called EK optimality. It's been also featured in Su's PhD thesis from the 2000s. And it's to use the Krieg invariance, but to have a correction term here. And the correction term depends upon the information matrix of this parameter theta and the derivative, the variance of the derivative of this y. Okay. Well, this is an approximation that is really an old one, which goes back to the literature to papers by Abt and even papers by Harvey in the 70s. So if you use this instead of the Krieg invariance, you get the bluish curves here. And they're higher, of course, because the variance is higher due to this correction. But what you can see is the bluish curves, they do not lend themselves to space filling as Krieg invariance does. Because if you shift this point, say this middle point here, up to the very, very right, you can shift it to the left, of course, too, you see that the Krieg invariance exceeds the Krieg invariances here, but this corrected EK variance, empirical kriging distance, this corrected EK variance is less than here. So this is a quite surprising effect, which means that you should really not do space filling when you have a small number of observations in these kriging cases. And but this should be, you can use this criterion. It's quite a I would say cumbersome criterion to use. You can use this criterion and do with it. But of course, when we're using something like ABCD, where we do not formulate anything about the estimation process, because the estimation process is in there in some sense by itself. Yes, we would not need to correct for anything. So ABCD should take care of that. Okay, so we just postulate what we want from the posterior. Especially what we want is a minimized prediction variance. Just state this, and ABCD should take care of it. Okay, so hopefully ABCD will not give us then space filling design in this setup. So we did this. I showed you this one. We can also play with other points. We can fix this point, and then we can look at the points up here. This is what Marcus did. What happens to the points, to the outside points when we fix the middle point. And here we get a map for the criterion, which is generated by ABCD. And you see that you are not going for space filling for these points, because now we're looking for pairs of points, okay, for the outer pair. So it's somewhere, it's optimizing somewhere here. So the optimum is not at the edges, but somewhere away from the edges. So this is taking care of it. We can take a closer look. If we fix another point, let's fix another point, x2 somewhere here, and we'll look at a one-dimensional representation of it. And the one-dimensional representation is here. Here we're using two different priors. I think it's not very essential which ones, but you see that in both cases, the optimal point is rather well identified by ABCD, and is also identified away from the border points. Okay. So this works very well. So you don't have to take into account problems that there are in the estimation process, because it will be taken care of by the simulation and the estimation itself. This is the fine thing about ABCD. Okay, you don't really have to think a lot about how to construct your criterion in a proper way. It needs to be a sensible one, of course. Okay, so let me come. How are we in time? Is it 15 minutes? Oh, I was too quick, because I have only one example left. It's the biggest one of all, and this is the example on spatial extremes. Again, spatial. You see my, see what I like to read, and it's taken. The whole example is taken from a paper by Erhard and Smith, I believe in computational statistics from 2012. Here the goal is, well, the goal of their paper was to model maximum monthly temperature and maximum monthly rainfall. And I'll show you later, what kind of problems arise here. And but we just took their setting and made a design problem out of it, because we said, okay, let us find the optimal configuration of these weather stations in such a way that you will you are in a good position, and the best position is to estimate these extreme cases of rainfall or temperature. Okay, so what they did, we just followed in the estimation part of the whole thing. We just followed exactly what they had and Smith did. So they assumed the max stable process for the probability model, particularly a so-called strata model. The margins are assumed to be transformed to unit Fréchet. And then we need, okay, then they used Whittle-Martin correlation function for the spatial field. And our purpose was, the idea for the criterion was to get the estimation of this spatial covariance function as good as possible. And we concentrated particularly on the very important range parameter of the spatial correlation function. The range parameter is the one that essentially describes at what distance observations stop being dependent. Okay. Usually you have some kind of spatial correlation function. Correlation is very high for nearby observations that are not very distant from each other, and then it declines. And at one point in time, you say, okay, the observations are far enough from each other so that we can assume that they're independent. And this is usually what is called the range. And obviously, the range is a very important parameter to estimate. So we concentrated here on estimating this range parameter in a Whittle-Martin covariance function. So the problem here is that there is no likelihood function available for this multivariate extreme value problem with the Schlatter function, Schlatter model, for dimensions greater than 2. This was already the reason why Erhard and Smith, used in their paper ABC to solve the problem. That's why we just took it. So, but the nice thing is you can simulate it from the model. Okay, you don't have access to the likelihood, but you can simulate the data. So now we need an optimality criterion. Okay, we can again do several things. Here we decided just to use the determinant of the posterior variance of the thetas, posterior variance covariance matrix, but if it's just one parameter, I think eventually we just use the range parameters and we just the variance, the inverse variance, which will be our utility function, or in Bayesian terms, we're using the posterior precision as the utility function. I believe it's a useful criterion in this respect, but I think Marcus played around with all kinds of criteria that can be used, and essentially there's not a big difference as long as you use a criterion which conforms to the Bayesian idea of the whole thing. Okay, so let's look at the data. This is the data that Werner and Smith also used in their paper. It's maximum sample temperatures. We're concentrating only on the temperature part of the data set from June or August from June 1st June to August 21st, from 1895 to 2009, measured on these 39 sites, which is the Midwest region of the US. And so we have 115 observations per site, and everything's quite well described in this paper by Smith. And we also made, here the obvious question now is, well, if we can get to choose a new station somewhere where to put it, okay? But this would be quite complicated to solve, because you would have to search, well, to find grid or whatever, through all these locations. So we decided, okay, let's rephrase the design problem slightly different. Let's look at the existing stations here and try to do a ranking on them. Let's see what kind of what of these stations are the most important ones, which ones are less important, and so on. Okay? So we basically reduce the grid of potential sites to the grid of existing stations, which made things, our calculations very much easier. So 39. We have just to look at 39 stations. Again, when you would look at and try to get a ranking, it would still be a formidable, you would have to look at all the possible rankings or whatever. So we decided to do first the following. We fixed two of the stations, one here and one here, because we thought these would be the stations that would be, well, essentially in any case for the spatial estimation, because they would be the two that are farthest apart from each other and cover the region. And then let's look for the next best station that needs to be in there. And then let's look for the next and the next and the next. So we're filling up design as it goes in the best possible way. Of course, this would reduce our computational task to a one step ahead method. So we would always only have to look for 1 out of 37 or 1 out of 36 or 1 out of 35 and so on besides. Yes. Otherwise, things wouldn't have been feasible. Okay. Okay, here the summary. So we consider only 3-point designs. We fix the points with the correct distance. Yes, and then we didn't use generated observations, but we used the so-called extremal coefficients as summary. This was the same choice that Werner and Smith had taken. Okay, so the triplet-wise extremal coefficients. This is fine. And each sample consisted of 1,000 independent replicates. So that was not too much. Quite fine. Okay, then we fixed also the seal and the smooth parameter after we did some estimation, because we had already data, of course, so we could, estimate them and fix them at some smooth values close to the estimates. And we had a prior for the range parameter, which was between 2.5 and 7.5. And then we used a different. We also used. Well, this is the prior we used first, so we used flat prior here, and then we made a second attempt with using the prior from the empirical distribution that we already had. Simulation numbers here, 2,000 for the integration step, and we're using the rejection sampler. So we keep 500, we always keep 500 from all these particles, and in the importance weight, we choose this effective sample size of 100. Good. So these are the rankings here for the precision utilities. So and we have two versions. The one is the basic rejection version. The other is the importance weight version. They don't differ very much. It essentially tells you that the next best observation, or next best site would be somewhere here in the middle. So here, this is 1, 2. You probably can't read it from back there. There's 1, 2, 3, 4, 5, 6, and so on. The worst stations here are the stations up here, 37, 36, 35. Those which are close to the one we had already in there. It's not a big surprise. It's the same here. Okay, so you just want to cover your area, by taking the next observation somewhere in the middle. And then we go on. By the way, sorry. This is the version with the because there's a slight difference when you use. This was our empirical distribution for the prior outer range parameter that was estimated from the data that already existed. This was the prior we used in the other case, and then we also used this empirical prior for a change. Also, I don't think that the effect was really very strong. Yeah, this is if the ABC sample is used as prior. Well, similar effect. Just one is here, 1, 2, 3, 37, 36, 35. This doesn't make a lot of a difference. And then we can, of course, continue. So we're doing now an augmentation of the design. So after the third point, now let's go to the fourth point. So we chose this point here, we fix it, and then we choose the next one. Okay, so where's the next one? Now the worst points really are here along close to this one, because this region is obviously covered now. We don't need this, so it wants to be somewhere here. Okay, this is the next point 1. There is a point 2, 3. There's quite a jump here, but also these points are quite low, 32, 30, something like this. Yeah, these are rankings, not the utilities themselves. Utilities are. It's not very visible, but I think the shade of the green reflects the amount of the utility here. Okay, and we can do the same. Now we can continue. Now we fix this point, and then we go, and then we'll have. Yeah, we fix this point, and then there is an exciting thing going on right now, because now the next point is, or the next point identified is here, 1. Which is the closest point to the middle point. And we interpret this as a similar thing as happened in the other example that we have here. That in these spatial things, it's always good to also get observations at close distances for getting the estimation of the correlation functions right. The correlation function is what we're interested in. Okay. So we need to get the information about the correlation function, not only at the large distances, but also at the small ones. So I think this is not a mistake of what's going on here. Looks a little bit strange and like a mistake, but I don't think it's really a mistake. So the next point would be here. But 2 would be here, 3 would be here. So it's quite flat right now. Okay, and 35, 34, and so on. So you could now use this for doing rankings. Obviously, it would be better, to be able to, use an algorithm that gives us the, let's say, overall optimal configuration of points. Yes, not the sequentially generated one. And we, in principle, could do it. But it's just unfeasible because we have to use, even outside of the outer loop that we have to use some kind of design algorithm that finds designs, goes from one design to the other one. And this, at the moment, is really not feasible for us. Okay, this was, I think, what I wanted to show you. And here I have some of the key references that I've mentioned. Yes, thank you for your attention and ask for questions. Thank you.
Okay, any questions for Werner?
In your Midwest temperature data, you said, to begin with, no, go back to the graph.
This one?
Well, you said that you fixed the top,
These two.
yeah, that one, and
Yeah.
but subsequently there was no points near the bottom in your designs. So,
These points were fixed.
yeah, but yeah,
Yeah.
so you had, I think it's design points near the top one,
Yeah.
but nothing.
Yeah, because we decided also, only to look at the existing sites, and there was no other existing site close to this one. I mean, you could, also change this and say you also look for, all potential sites you would have to look at a grid or something for it. But we're already at the, verge of feasibility here, computational feasibility, so this would make things very much harder.
In the quadratic regression example, go one more slide, go back.
Oh, okay. Yeah.
Do you fix sigma squared, or is it unknown?
This is, here it's fixed. It's fixed. I don't think it makes a difference, does it? It won't make a difference, yeah.
It won't make a difference to the exact optimal design, but I
Yeah.
thought it might affect the performance of the ABCD, because if it's big,
If it's big, it could obscure the things,
Yeah.
yes. Well, I'm not sure, I don't remember this example very well, whether I probably think we fixed it at once.
In this example, when you show the results, do you use the sampling from the prior method or the important sampling method?
Here, we
Yeah.
used just a simple rejection sample, the one that I showed at the very beginning, because this was the first example that we did, and there were no refinements done at that stage. So this is really the absolute simplest approach here, this one.
Any other questions?
In the spatial stations example, given that your data are maximal, do you alter your model to handle that the data are maximal?
They're using the model. The model is a model for maxima. It's a max stable process, Schlatter model. It's a model for maxima. Yeah.
Okay.
Yeah.
So it's basically a sort of latent variable model where you've got a Gaussian field that defines the parameters for each of those extreme value distributions. Is that correct?
We're probably
Basically smoothing the parameters of the extreme value distribution.
I'm not sure I quite get the gist of the question. I think we're not using a random field we're using a random field for the maxima.
Okay.
For modeling maxima rather than. I think I get what you mean. We could, of course, model the field itself and then only look for the maxima.
Okay.
That's we could do both, but we're not doing this here.
Okay.
Yeah.
So I had a quick question on this. I wasn't quite sure what the dimension is. It's dimension squared from 2. What is the dimension in this?
Well, you mean this dimension?
Yeah.
I think it's the. Let me see. It's the number of extreme values that you're looking at. It's probably here. It's dimension. I think it's just the number of extreme values that you're looking at. So it could
Right,
be here, it
okay.
could be,
So it's
it would be 2 in this case. But.
Okay, any last questions?
But it potentially could be,
No? Okay, well, let's thank Werner again.